Okay, so last time we were talking about the basic principles of NMR spectroscopy. Let's have a quick recap. NMR is the study of nuclei that are associated with some amount of spin. This is what we discussed last time, and this is the basic equation from which all of this technique is based on. So mu is the magnetic moment, and that is equal to gamma IH. Gamma, as you already know, is the magnetodirect ratio. That is the ratio of the magnetic moment to the angular momentum. I is the spin and H is the Planck's constant. Now those nuclei which have odd atomic number or odd mass number, or both of them as an odd value, they are associated with some amount of spin, and that is why we can study them in NMR spectroscopy. Magnetodirect ratio or gyromagnetic ratio we discussed last time. It's a characteristic property of each and every nucleus that is associated with a certain amount of spin, and because each of these nuclei, they have different mass and charge, that is why their angular momentum would be different and their response towards the magnet would be different. That is why each nucleus has a different magnetodirect ratio. These are some nuclei which we can or cannot study in NMR. So we have written these two types in different color. That is to indicate that we will be focusing on only these two types of nuclei, that is proton and carbon-13. Both of them has a spin equal to half, and both of them have an odd number of protons and even number of neutron in case of proton, and even proton and odd neutrons in case of carbon-13. But luckily both have the same spin quantum number, and that is why whatever we discuss for proton is also applicable to carbon-13. But again, there is a slight difference in terms of the response towards the magnet. The magnetic direct ratio is different for both proton and carbon-13. So this is the equation from which you can find out or calculate the spin states. If spin is half for both proton and carbon-13, that means it can have two possible spin states. And these two spin states arise when you place these nuclei in a magnetic field. So you can see here, when the magnetic field is off, they are randomly oriented in all possible directions. But when you turn on the magnet, when this B0 has some value, then you can see that they organize themselves, they rearrange themselves in all possible spin states. Now, because for proton and carbon-13, we have two possible spin states, so they can arrange themselves in two spin states. You can see some of them are aligned along the direction of the applied magnetic field, and some are against the direction of the applied magnetic field. This B0 by default will always be pointing up in the literature if you read it. So the first thing that happens when you turn on the magnet is that they arrange themselves in all possible spin states, and the second is that they start precessing with a particular frequency. Precession, as I have told you, is a special type of movement these nuclei have under the influence of magnetic field, and that is like a top before it's about to fall. And so it's a wobbling movement which we call precession, and this happens with a particular frequency which we write as omega, that is the Larmor frequency or precessional frequency or resonance frequency, that is in radians per second, which is equal to gamma B0. Gamma again is magnetodirect ratio. So if you are talking about a particular nucleus and you are talking about its Larmor frequency under certain conditions of magnetic field or magnetic field strength, so you have to take this gyromagnetic ratio as a constant. It doesn't depend upon the magnetic field. So it's a constant always. If you remove this constant, omega is directly proportional to B0. And that means that when you increase the strength of the magnetic field, the Larmor frequency or the precessional frequency will increase. And this is also known as the resonance frequency. If you remember the first lecture, we said that resonance takes place, and that is when you apply radio frequency. So resonance always takes place when two waves are interfering with each other. So when they have the same frequency, they will match with each other, and you can observe resonance then. And you can see these nuclei, they move around this axis in a particular direction to observe this precession. And the direction of this precession is determined by the right hand rule. So if the thumb of your right hand points in the direction of the applied magnetic field, then the curved fingers will point in the direction of precession, or your nucleus will move in the direction of your curved fingers, and this is how it looks like. So it's the nucleus that is precessing around its axis. You can see its center of gravity still lies on the axis, but above and below the center of gravity, it forms a circular path around this axis, and it again is in a particular direction that is determined by the right hand rule. So these nuclei, they arrange themselves in all possible spin states, and it starts precessing with a particular frequency. Now, what is meant by arranging themselves in all possible spin states? So when you turn on the magnet, you have two possible spin states for proton and carbon 13, because both of them have spin equal to half. So when B naught is equal to 0, you see all the directions, all the orientations, they are degenerate. There is no difference of energy between these directions or orientations. But when you turn on the magnet, or you start increasing the magnetic field, you see that a gap develops between these nuclei, or the spin states of these nuclei. So some of them are in a higher energy state, and some of them are in a lower energy state. The lower energy state is known as the plus half state, and the higher energy is the minus half state, or we can also call them as alpha and beta states in NMR. The difference of energy, that is del E, between these two spin states is directly proportional to B naught, as you can see from this diagram as well. When you increase the magnetic field, the difference of energy increases. So del E is equal to K B naught. K is the proportionality constant. If you remove it, del E is directly proportional to B naught. And you already know another equation, that is E, or del E, is equal to H. H again is Planck's constant, and mu is the frequency. Which frequency? The radio frequency. So del E is also directly proportional to the frequency. What it means is that if del E is larger, if the difference of energy between alpha and beta states is higher, then you have to provide a larger frequency from outside so as to observe resonance. Why is that? Because del E is directly proportional to B naught. So if del E is higher, that means automatically B naught is higher. If B naught is higher, Larmor frequency is higher. So to match that higher Larmor frequency, you have to provide a higher radio frequency as well. So you have to understand these relationships. Again, I told you last time, the relationship between B naught, Larmor frequency, and again here, del E. Del E is directly proportional to B naught. What are the other factors that may affect the value of this del E, or the difference of energy between these spin states? So you see here that we just saw that the difference of energy between the spin states is directly proportional to B naught, or we can say that it's a function of the applied magnetic field. So you can write it in this form, which is also equal to H min. Now this difference of energy for different types of nuclei also depend upon another factor, that is a constant, that is the gyromagnetic ratio of these nuclei. We can say that del E is a function of the B naught as well as the gyromagnetic ratio. And this is very important. This energy gap between the two spin states of proton and carbon 13, this is very important. Important in what sense? It's important in terms of signal generation. Del E is dependent upon gyromagnetic ratio. That means del E automatically would be higher, and that will directly or indirectly affect the signal intensity as well. Now, the angular momentum, because each of these nucleus has a different angular momentum. When you place them in a particular magnetic field, each of them have a different angular momentum. Why? Because they have different charges and they have different mass value. So each of them have a different angular momentum, and that is quantized. So you can quantify the angular momentum. So the final equation that we have is del E is equal to the gyromagnetic ratio multiplied by h by 2 pi into B naught, which is also equal to hb. Now if you rearrange the equation for mu, that is the radio frequency. So we come up with this equation, that is gamma B naught divided by 2 pi. Now what does this mean? Gamma for a particular nucleus is constant, gyromagnetic ratio is constant, 2 and pi, these are constants. So if you take them as constants and convert this equation into proportionality, mu is directly proportional to B naught. So Larmor frequency, del E and radio frequency, all of them are directly related to B naught. So mu here is directly proportional to B naught. What it means is that if you provide a larger magnetic field, a magnet with a higher strength, it means that you have to provide a higher radio frequency. Or in other words, you can say that resonance will take place at a higher frequency. So this is logical, it's understandable, but we have proven it with an equation here, and you can see that mu is directly proportional to B naught. So here we have this equation, that is gamma h B naught. So this is equal to h mu as well. Now this frequency mu, it corresponds to the light in radio frequency range when B naught is in Tesla. So if you take B naught in Tesla, then the light will correspond to the frequency that is in the range of radio frequency, which means that these nuclei will absorb light of a frequency that is in the range of tens to hundreds of megahertz. So these nuclei will absorb light in this range, in the range of tens to hundreds of megahertz. Last time I told you that your NMR is a big, expansive radio. It operates in the same way as you operate your radio. So you already know that your FM radio frequency is from about 88 megahertz to about 108 megahertz. So it more or less operates in the same fashion. Your radio operates in the reverse direction, right? So when you tune your receiver, your radio set receiver on exactly the same frequency at which your channel is transmitting, then you will be able to hear the songs or the news or whatever programs are being transmitted. If you deviate from that frequency, resonance will not take place and you will hear just the noise. So what you are doing is you are tuning your receiver. You are tuning your receiver. You are not tuning your transmitter. It's different in case of NMR. Here, the frequency of the receiver is constant. You can tune your transmitter, but the frequency of the receiver is constant. And who is the receiver in case of NMR? Who is the receiver? The nuclei. The nuclei are the receivers. So each nucleus has its own Larmor frequency under that particular magnetic field. For example, we're talking about proton. These protons will have the same frequency under the same magnetic field strength. So you can tune your radio frequency transmitter that is available to your NMR machine and you have to tune it to exactly the same frequency at which your protons are precessing. And that is the beauty of NMR. Why? You have a molecule. Molecule may, you can have carbon in the structure, you can have hydrogens in the structure, you can have nitrogen, oxygen, all these different types of nuclei are present in a molecule. But when you put your sample inside the machine and you tune your radio frequency transmitter at a particular frequency, you see only one type of nuclei. So you get a spectrum for protons only or hydrogens only, you don't see any carbons. That doesn't mean that your compound does not have carbons. You cannot see them. Why you cannot see them? Because you are not resonating your carbons, you are only resonating your protons. You have tuned your radio frequency transmitter to the frequency of protons only. Why they have different Larmor frequencies? Because each of them have a different gyromagnetic ratio. Each of them have a different response towards the magnet. So NMR is a big expensive radio and it operates at the same principle but in a reverse direction to your radio set. So now we have discussed the effect of B naught on the nuclei. What happens is that they arrange themselves in all possible spin states. An energy gap is developed between these spin states, that is del E, and they start processing with a particular frequency. And then we discussed about the radio frequency. The radio frequency is also directly related to B naught, because to match that higher Larmor frequency, you have to provide higher radio frequency as well. And we will see that in a moment why. So, this diagram shows the absorption of energy. From where does this energy come? From the radio frequency transmitter in the form of radio frequency. So we have B naught, again pointing up, and you have these nuclei in a lower energy state, that is the alpha state or the plus half state. And in a plus half or alpha energy state, these nuclei are aligned along the direction of the applied magnetic field. Yes. When you provide them with certain amount of radio frequency, is this random or is it quantized? It's quantized. You have to provide a specific amount of frequency, a specific value of frequency. And you already know that if B naught is higher, del E is higher. So if del E is higher, you have to provide a more energetic radio frequency. Right? So from this equation, you know that del E is directly proportional to the radio frequency. So you have to provide radiation that has exactly the same frequency or energy that is equal to del E. So we have this nucleus in the lower energy state that is aligned along the direction of B naught. We provided with a particular amount of radio frequency that matches the del E between these two states. What happens is that these nuclei, they flip. They were aligned along the direction of the applied magnetic field. When you provide them energy that matches del E, they flip. So they go from plus half state into minus half state. You can say that they jump from a lower energy state to a higher energy state. Jumping means ke flipping ho jati hai. So they flip from plus half state into the minus half state. That is absorption of energy. और इसी को हम क्या कहते हैं? Resonance कहते हैं. So nuclear magnetic resonance. Nucleus की study under the influence of magnetic field to record the resonance that occurs by absorption of radio frequency. There always is some population in the alpha state and some population in the beta state. So what is the population density of these nuclear states? You just saw with the help of this diagram that when you provided energy, when resonance takes place, these nuclei jump from lower energy state to a higher energy state. That is, they jump from plus half spin state to a minus half spin state. Or in other words, you can say that they flip from plus half to minus half spin state. So do all the nuclei, they jump into the beta state? No, there is certain amount of population still in the alpha state and some are in the beta state. Now what is that population density, or what is the difference of population, or is it the same population in alpha or beta state? You already know that we can calculate del E from the strength of the magnet. You know the strength of your magnet. So, for example, we have a magnetic field that operates at 1.41 Tesla. Then, for protons, for hydrogens, resonance will take place at 60 megahertz. What does it mean? So, if you have an NMR machine that has a magnet installed in it, and its strength is equal to 1.41 Tesla, and you put your protons inside this magnetic field, an energy gap is developed between the alpha and beta states, and that energy gap would be high enough or large enough that will require, or that will allow you to operate your radio frequency transmitter at 60 megahertz. So the energy of the radiation, whose frequency is 60 megahertz, is exactly equal to the energy gap between the protons, or the spin states of the protons, under the influence of a magnet or magnetic field that is operating at 1.41 Tesla. बात समझ में आ रही है कि अगर हमारे पास मैग्नेट कितनी स्ट्रेंथ का हो, 1.41 टेस्ला, तो जाहिर है आप प्रोटॉन्स रखेंगे, एनर्जी गैप डेवलप होगा. उस एनर्जी गैप को फैलाने के लिए, टू मेक योर न्यूक्लियाई जंप फ्रॉम अल्फा स्टेट टू बीटा स्टेट अंडर दीज कंडीशंस, कितनी एनर्जी आपको प्रोवाइड करनी है? एग्जैक्टली उतनी ही ना जितना एनर्जी गैप है. अब एनर्जी गैप तो आपको नजर नहीं आ रहा, आपको स्पिन स्टेट्स नजर नहीं आ रही बाहर से, तो आप कैसे बताएंगे कि कितनी? आपने ट्यूनिंग करनी है, और एक वक्त ऐसा आएगा कि आपको रेजोनेंस नजर आएगी, और वो रेजोनेंस किस फ्रीक्वेंसी पे नजर आएगी? 60 मेगाहर्ट्ज. इसका मतलब है कि 60 मेगाहर्ट्ज की जो एनर्जी है, फ्रीक्वेंसी से आप एनर्जी कैलकुलेट कर सकते हैं ना, इज इक्वल टू एच म्यू से आप एनर्जी कैलकुलेट कर सकते हैं. तो इस इक्वेशन से, या E इज इक्वल टू एच म्यू से आप E मालूम करेंगे. किस चीज की E? इस रेडियो फ्रीक्वेंसी की एनर्जी, which will be exactly similar to del E. तो del E आप मालूम कर सकते हैं, ठीक है. सो जिस फ्रीक्वेंसी पे रेजोनेंस होगी या जिस एनर्जी पे रेजोनेंस होगी, इसका मतलब है उतना ही एनर्जी गैप है. एंड दैट इज व्हाई वी से इट इज क्वांटाइज्ड, कि आप इसको क्वांटिफाई कर सकते हैं, राइट. नाउ at 60 megahertz under 1.41 Tesla, nuclei jump from lower energy state to higher energy state. But for 1.41 Tesla, the energy difference is very small. Del E is directly proportional to B naught. So if B naught is smaller, del E is smaller. So 1.41 Tesla is a small magnetic field, and that means del E would be smaller, which means that it is easier for nuclei to jump from alpha to beta state. For this magnetic field strength for 1.41 Tesla, because the energy gap is smaller, both alpha and beta states would be populated. There would be some nuclei in the alpha state, and there would be some nuclei in the beta state. But what is the population density? Is it the same for alpha and beta states? No. There always is some small excess of nuclei in the alpha state. This is natural. You know that everything wants to be at a lower energy state, because that is a state of stability. The same is the case here. कि energy gap ज़्यादा हो या कम हो, there always is a small excess of nuclei in the lower energy state, which we call the Boltzmann axis. This is from Boltzmann distribution law, that if you have two possible spin states, a lower energy state and a higher energy state, the lower energy state would be slightly more populated than the higher energy state. And this small axis is very important in terms of the generation of signal in NMR. Now we can relate this del E, or the population density, to the strength of the signal. How? So, if we have an instrument that is operating at 60 megahertz, we already know that the magnetic field would be 1.41 Tesla. We are operating at 1.41 Tesla, and the radio frequency required for resonance is 60 megahertz. So at this frequency, if you have 1 million nuclei that are present in the beta state, in the higher energy state, 1 million plus 9 nuclei will be present in the alpha state. And it's a very small axis. This axis is negligible, but still these 9 nuclei are important for the signal intensity. These 9 nuclei, which are in axis in the alpha state, they allow us to observe resonance. So now you know the importance of axis nuclei in the alpha state. What it means is that if there is no axis nuclei in the alpha state, then we won't have any signal. We will not see any signal. Why? Because we won't observe any resonance. Because it's only the axis nuclei that allow us to observe the resonance. बाकी जो 10 लाख है, 10 लाख ये, 10 लाख ये एक दूसरे के इफेक्ट को कैंसिल करें. 10 लाख अल्फा स्टेट में है, ऊपर की तरफ है. 10 लाख बीटा स्टेट में है, नीचे की तरफ है. इनके मैग्नेटिक मोमेंट्स एक दूसरे को कैंसिल कर रहे हैं. लेकिन अल्फा स्टेट में 9 न्यूक्लियाई ऐसे हैं जिनके मुकाबले में ऊपर 9 न्यूक्लियाई नहीं है. तो जो कंबाइंड इफेक्ट है इन 9 न्यूक्लियाई का, दैट इज एक्चुअली रिस्पॉन्सिबल फॉर सिग्नल जनरेशन. बाकी 10 लाख जो है वो बिल्कुल बेमानी होगी. So what does that have to do with the del E, or the magnetic field strength? If del E is higher, the number of axis nuclei will increase. These nuclei would be reluctant to go up. If the nuclei are reluctant to go up, they would be present in the alpha state. But some of them will still jump into the beta state. So an energy, a population gap is still there, axis nuclei are still there, and the number of these axis nuclei are higher than in a case when del E is smaller. And I told you, okay, these axis nuclei are important for signal generation, or the strength of the signal. So if you have a large number of axis nuclei, the signal will be more strong. If you have a small axis of nuclei, the signal will be weak. If there is no axis nuclei, no signal. Now this table shows you the difference between or the relationship, or it's a comparative analysis of machines operating at different frequency. So if you are operating at 20 megahertz, under these conditions you will have only 3 nuclei in axis. At 40 it is 6, at 60 we just saw that it's 9, but when you go down to 600 megahertz, axis nuclei are equal to 96. Now we have an appreciable amount of axis nuclei in the alpha state, and that means a stronger signal. So now we know that the population density in the alpha and beta state, that is more or less related to the energy gap. If you have a higher energy gap, which means you are operating at a higher frequency or higher magnetic field, then the difference of population or the excess nuclei will be in higher number in the alpha state, and that means a stronger signal. Now, how does that signal actually is generated? In two words, this NMR signal, as I told you earlier, is because of the excess population. If there is no excess population in the alpha state, there would be no signal. The state where there is no difference of population between the alpha and beta state is known as a saturated state. That condition is known as saturation. So if the system is saturated, which means that the number of nuclei in alpha state are exactly equal to the number of nuclei in beta state. In other words, if the population of alpha and beta state is similar, we say that the system is saturated, they have equal population, and there is no signal. So for a net signal, for a net positive signal, you must have some excess of nuclei in the alpha state. And how does that happen? We have these two states right here, the alpha and beta states. So originally, some of these nuclei would be in alpha, others in beta state when you turn on the magnet. And later on, when you turn on the radio frequency transmitter, that is when radiation induces upward transition. These nuclei jump from alpha to beta state. This jump from alpha to beta state is known as resonance. This is known as resonance. So a jump from alpha to beta state is known as resonance. But at the same time, when some nuclei are jumping from alpha to beta state, at the same time, some nuclei, they jump back from beta state to the alpha state. And this jump from beta to alpha state is known as induced emission. And why does this happen? This happens because of the radiation, because it induces both upward and downward transition. And why would some nuclei jump back from beta to alpha state? So as to restore the excess population. So as to restore the excess population. And it's a continuous process. Continuous process chal raha hai. But at a particular moment, there always is slight excess of population in the alpha state. If you have a condition in which you have equal population in both the states, how can we achieve this state, the saturated state? You can achieve this saturation if you provide energy continuously. And we are providing energy in the form of radio frequency. We are providing energy in the form of radio frequency. So if you provide radio frequency continuously, these nuclei will jump from alpha to beta, beta to alpha continuously, and a stage will come where the population difference would be zero, or in other words, both the alpha and beta states, they will have equal population. There will be no excess population, and that is where you won't observe any signal. So for a net signal, you must have a slight excess of nuclei in the alpha state. Now coming back to the question asked by you, I think, that if all these nuclei, they absorb the same frequency, then why we are performing NMR? Or what is the importance of NMR? How it helps us in differentiating between all these nuclei. So that is what we will discuss now, is that resonance means the absorption of energy. Which energy? This energy is in the form of radio frequency. So you are actually providing radio frequency, And that radio frequency or radiation has a particular frequency. Which frequency? You have a large range of radio frequency. Which frequency is actually absorbed? Which frequency will be absorbed? That radio frequency that matches the precessional frequency of the nucleus. Which nucleus? Which we are studying. We are actually talking about proton right now. So a proton will absorb radio frequency that matches exactly with its precessional frequency under a particular magnetic field strength. But your question still remains there, that if we are talking about one type of nucleus, that is proton, all of these protons have the same gyromagnetic pressure. They have the same magnetic moment. They have the same angular momentum. They have the same Larmor frequency. So if all of them have the same Larmor frequency under the same magnetic field, they should absorb the same frequency. So the next question is that do all these nuclei have the same Larmor frequency or same precessional frequency under a constant magnetic field? No. They do not have the same frequency. But again, why? Because of that interference. Because of the interference. Why these nuclei do not observe resonance at the same frequency? Or in other words, why these nuclei, they do not absorb the same frequency? Because each of them have a different precessional frequency. Each of them have a different Larmor frequency. Again, the question why? That is because of very common phenomenon that we call shielding and deshielding. So what happens inside a molecule is that, you see this diagram here, right in the center we have the nucleus. The nucleus which we are studying, which is under observation. And you know that this nucleus, this hydrogen, this proton is part of a molecule. This hydrogen would be attached to a carbon atom. That carbon would be in turn attached to another carbon. So it has a network around it. This hydrogen has a network of different types of atoms and elements around it. And it has a certain amount of electron density around it. Each of these nuclei, these hydrogens, have some amount of electron cloud surrounding it, or electron density around it. And you know that electron density means current. You know that when current flows inside a wire, it produces a magnetic field. So this electron density, which you can see from this direction, is moving in a particular direction. From this circle, see the arrows here, it's moving in a particular direction. And when electrons move, we call it a current. And you know that when current moves, it produces its own magnetic field. And these lines are the lines of the magnetic field that are generated because of this electron density that is present around the nucleus. So we have the applied magnetic field pointing upwards again. We have the nucleus here. Because of this magnetic field, these electrons, or the electron density, is made to circulate in a particular direction, which you can see from this circle here. And when these electrons move, or this electron density moves in this direction, it produces its own magnetic field. And these magnetic field lines show the direction of this magnetic field. And it's actually all around this nucleus. So these lines are actually all around this nucleus in a particular direction. This magnetic field that is generated because of the electron density around this nucleus is known as the induced magnetic field. This magnetic field is the induced magnetic field. Now, this magnetic field or the induced magnetic field opposes the applied magnetic field. You can see the direction of these lines right here in the center where this nucleus lies. The direction of these magnetic field lines is against the direction of the applied magnetic field, which means that this small magnetic field is opposing the applied magnetic field, and in turn it reduces the effect of this applied magnetic field on this nucleus. And what is the effect of the applied magnetic field on nucleus? It makes it to precess with a particular frequency, that is the Larmor frequency. So if this induced magnetic field is reducing the effect of the applied magnetic field, it is actually reducing the Larmor frequency of this proton. Samajh aa raha hai? Yes. Is that understood? Yes. If this induced magnetic field is reducing the effect of the applied magnetic field, it's actually reducing the Larmor frequency of this proton. Now, we are providing B0, and at a particular B0, this proton should have a particular Larmor frequency, which you were asking. At this particular B0, this proton must have a particular Larmor frequency. Why these protons then absorb different radio frequencies? It is because of the fact that all of these protons, they are not experiencing the same applied magnetic field, because they have a different electron cloud around them, or electron density around them. And if they have different electron density around them, they will have a different strength of the induced magnetic field around them. And if they have different strengths of the induced magnetic field around them, they will have a different reduction in the strength of the applied magnetic field. And this reduction is actually calculated from here. So what this nucleus experiences is not B0. It's B effective. B effective is that effective magnetic field which actually imparts a certain amount of Larmor frequency to this nucleus. So B effective is equal to B0 minus B induced. This B induced actually is a very weak magnetic field, but it is enough to reduce the effect of B0 to a certain amount, and then the magnetic field that each of these protons experience is different from the other. Now these protons, if they are under different chemical environments, what do you mean by chemical environment? If they have different atoms attached. For example, we have a hydrogen that is attached to a carbon atom in a molecule. We have a hydrogen that is attached to an oxygen. We have a hydrogen that is attached to a nitrogen. We have a hydrogen that is attached to something else in the molecule, to sulfur in the molecule. Each of these hydrogens will have a different electron density around them. When they have different electron density around them, they will have a different strength of they will have a different strength of induced magnetic field around them. If they have a different strength of induced magnetic field, the reduction in the strength of B0 will be different, which means that B effective is different for all these protons which are attached to carbon, oxygen, nitrogen, and so their Larmor frequencies would be different. If their Larmor frequencies are different, they will observe resonance at a different frequency, or they will absorb radiations of different frequencies. They will not absorb radiation of the same frequency. And this absorption of radiation at different radio frequencies allow us to differentiate between these two. And then we know if we have these three different types of hydrogens, one that is attached to carbon, the other is attached to oxygen, the other is attached to nitrogen, and they have different B effectives, they have different Larmor frequencies, they have different resonance frequencies. From that resonance frequency, we can determine, or we can say, or we can differentiate that this hydrogen is attached to carbon, this is attached to oxygen, this is attached to nitrogen. And that is the information that you get from the resonance frequency, or NMR in a larger sense, that you can actually tell that my molecule may have a hydrogen that is attached to carbon, to oxygen, or nitrogen. Right? So this is how these nuclei can be differentiated. Now, how can we determine the direction of the lines of the induced magnetic field? That again is from right hand rule. So if the thumb of your right hand, it points in the direction of the flow of current, then the curved fingers will point in the direction of the magnetic field. So let's apply this rule to this diagram. You can see here, this is the direction of the flow of electrons or the current here, right? If this is the direction in which your thumb points, the magnetic field lines will be pointing downwards here because your curved fingers show the direction of the applied magnetic field. And this is not in a single direction, it's actually circular. So it's actually like this, going upwards away from the nucleus. Same is the case here. Right in the area where your nucleus lies, the direction is downwards and then it forms a circle. So you have areas where the direction is the same as that of the applied magnetic field, and we have areas where the direction is against the direction of the applied magnetic field. So in this area, these lines or this magnetic field is aligned along the direction of the applied magnetic field, but in this region where your nucleus lies, the magnetic field lines are opposing the applied magnetic field. यहाँ B effective ज़्यादा होगा, B effective ज़्यादा होगा तो लार्मर फ्रीक्वेंसी ज़्यादा होगी, लेकिन यहाँ तो प्रोटॉन है नहीं, न्यूक्लियस तो यहाँ है, जहाँ न्यूक्लियस पड़ा हुआ है वहाँ डायरेक्शन ऑपोजिट है, तो डायरेक्शन ऑपोजिट है तो फिर आप माइनस करेंगे, बी इफेक्टिव कम होगा. If B effective is lower, Larmor frequency would be lower. So let's have a comparison and then we sign off. So these are the resonance frequencies and some other information of some of the common nuclei. So we have proton here, deuterium, carbon-13 and fluorine. We have the abundance, the natural abundance for proton, that is 99.9%. For deuterium it's 0.01%. For carbon-13 it's 1.1% and fluorine is 100%. Right? And then we have the magnetic field strength. So if you provide a certain amount of magnetic field, it will make these nuclei to resonate, to precess with a particular frequency. This is the frequency in megahertz, and here is the charomagnetic ratio. So charomagnetic ratio is constant under all conditions. So you can see here, we have one value for proton, one for deuterium, one for carbon-13, and one for fluorine. It doesn't change. So this is a constant. Now, if we have a magnetic field equal to 1 Tesla for proton, its Larmor frequency would be 42.6. Again, this is ideal. When there is no interference, when there is no induced magnetic field, when there is no electron density that interferes with the applied magnetic field, right? At 1 Tesla, the Larmor frequency of proton is 42.6 megahertz. That means that resonance will take place at 42.6 megahertz. 42.6 megahertz. At 1.41 Tesla, we just saw that the resonance frequency is 60 megahertz. If you increase the magnetic field to 2.35, then the frequency is 100. At 7.05, it is 300 megahertz. The gyromagnetic ratio remains the same. Even if you change the magnetic field, there is no effect on the gyromagnetic ratio. Now let's go down to carbon-13, because we will be focusing on these two nuclei in this course. We will compare these two. If you have carbon-13, which is 1.1% in nature, इसकी natural abundance 1.1% है, and you provide this carbon-13 with a magnetic field that is equal to 1 Tesla. The Larmor frequency would be 10.7 megahertz. That means the resonance frequency is 10.7 megahertz. If you have a magnetic field of 2.35 Tesla, then it is 25. If you have a magnetic field of 7.05, then it is 75. Again, the gyromagnetic ratio remains the same under all conditions. Now, let's compare proton and carbon-13. I just told you before that whatever we are studying for proton is applicable to carbon-13 as well, because luckily they have the same spin quantum number, so they have the same spin states, alpha and beta states. So जो भी हम पढ़ रहे हैं proton के लिए, that is applicable to carbon-13. But there are slight differences which I told you earlier, and this is the table that will let you differentiate between proton and carbon-13. The first difference is its natural abundance. So you can see that in nature, proton or protium is 99.9%. And carbon-13 is only 1.1%. Carbon-12 is almost 99%. Carbon-14 फिर उससे भी कम, right? Which means that it is easier to find a proton in a molecule or a protium in a molecule than to find a carbon-13. If you have a molecule, for example, a simple molecule of methane, CH4. So you know that you have 1 carbon and 4 hydrogens. To know that this molecule has 4 hydrogens, all of these 4 hydrogens have to be proton. So there are 99.9% chances that a hydrogen inside this molecule is protium or proton, or the nucleus of that hydrogen is a proton. It does not have any neutron. But this same molecule also has a carbon. To observe or to see this carbon, it has to be a carbon-13. Because if it is carbon-12, you cannot see it. The only way you can see this carbon in methane is when it is a carbon-13. Now there is only 1% chance of this carbon being carbon-13. What does this mean? If you have, for example, 100 molecules of methane, if you have 100 molecules of methane and you select 1 hydrogen out of the 4, the 99.9% or 99.9 molecules out of those hundreds will have that hydrogen as a protium or a proton. The nucleus would be proton. But out of those 100 molecules, there will be only 1 molecule in which the carbon would be carbon-13. Rest of the 99 will have carbon as carbon-12, which means that for you, those 99 molecules are useless. If you want to see carbon-13 in methane, those 99 molecules are useless. Only that 1 molecule is useful. So you have equal number of molecules, 100 for analyzing proton, 100 for analyzing carbon-13. Out of those hundreds, 99.9 molecules are useful for you guys to see proton, but only 1 of those 100 is useful for you to see carbon-13. Which means that because of the higher natural abundance of proton, it is easier to be found. If it is easier to be found, its signal strength would be strong, higher. Its intensity will be higher, which means that you need to have more molecules so as to have more chances of carbon-13 being there. For example, if you have 200 molecules, so there are chances of 2 molecules of methane having a carbon-13 out of 200. क्योंकि 1% है ना, so out of 200, 2 would have carbon-13. Only those 2 carbons or those 2 molecules will give you a signal for carbon-13. Rest of the 198 are useless because they have carbon-12. If you have 300, 3 molecules will have, there are chances of 3 molecules having carbon-13. If you have 4 molecules, then 4, 5, 6 and so on. So as to have 99 carbon-13s, जिस तरह प्रोटॉन में था, प्रोटॉन में तो 100 में भी आपको 99 मिल रहा है. So as to have 99 carbon-13s, you can count the number of molecules that you need for that. So to bring the signal intensity at par with proton, carbon-13s are the molecules for which you want to see carbon-13 must be higher in number. Higher number का मतलब है you need a larger quantity. So a proton NMR spectrum, a good proton NMR spectrum requires less quantity of your sample, but a good carbon-13 spectrum requires larger quantity. That is because of its lower natural abundance. And then we come to the Larmor frequency part. And this is very interesting and very useful. And that is the beauty of NMR, which I told you earlier last time, that you have carbons, oxygens, nitrogens, hydrogens all present in the same molecule. But when you place this molecule in your NMR tube and you turn on the magnet with any of these magnetic field strengths, you only see proton in the spectrum, or you only see carbon-13 in the spectrum, or you only see fluorine or deuterium in the spectrum. Why is that? Because each of these different types of nuclei under the same magnetic field strengths will have a different Larmor frequency. You can see each of them has a different Larmor frequency at the same magnetic field strength. And if each of them have a different Larmor frequency, to see proton, you have to tune your radio frequency transmitter at 42.6 megahertz if the magnetic field strength is 1 Tesla. And the same molecule under the same magnetic field strength in the same machine, if you want to see carbon, you have to tune it to 6.5. If you want to see deuterium, you have to tune it to 6.5. If you want to see carbon-13, you have to tune it to 10.7. If you want to see fluorine, you have to tune it to 40. वहां आप क्या चीज ट्यून करते हैं? क्या चीज ट्यून करते हैं? रिसीवर को ट्यून करते हैं. यहां आप क्या चीज ट्यून करेंगे? ट्रांसमीटर को ट्यून करेंगे. आपने क्या चीज देखनी है? प्रोटॉन देखना है, ट्रांसमीटर को ट्यून करेंगे. मैग्नेटिक फील्ड को आप चेंज नहीं कर रहे. दैट इज 1 टेस्ला इन ऑल केसेस. आप किस चीज को ट्यून करेंगे? ट्रांसमीटर को. ट्रांसमीटर को अगर आपने प्रोटॉन देखना है तो 42.6 पे ट्यून करें. नहीं देखना प्रोटॉन, अच्छी बात है, उसी सैंपल में आप सैंपल भी ना निकालें. आपने सैंपल इंसर्ट किया हुआ है, यू ट्यून योर रेडियो फ्रीक्वेंसी ट्रांसमीटर एट 42.6, यू विल सी प्रोटॉन्स. कुछ भी चेंज ना करें, सिर्फ रेडियो फ्रीक्वेंसी ट्रांसमीटर को रीट्यून करें at 10.7 megahertz. This will show you, if you tune your radio frequency transmitter at 10.7 megahertz, you will see carbon. If you tune your radio frequency transmitter at 6.5 megahertz, you will see deuterium, and so on. तो ये तो आपने डिसाइड करना है कि आपने क्या चीज देखी. And this is the beauty of NMR, that you don't see all of these nuclei at the same time because they have different Larmor frequencies. If all of these nuclei had the same Larmor frequencies under a particular magnetic field strength, NMR would be useless. NMR would be useless. फिर ये useless होगा. और अगर इसमें जो induced magnetic field की कहानी है वो भी ना होती तो फिर NMR useless होगा, क्योंकि फिर तो प्रोटॉन की सबकी फ्रीक्वेंसी सेम होती, कार्बन की उसके साथ सेम होती, तो सब एक ही फ्रीक्वेंसी पे नजर आते हैं. आप प्रोटॉन और कार्बन के दरमियान डिफरेंशिएट नहीं कर सकते तो फिर दो प्रोटॉन्स के दरमियान कैसे डिफरेंशिएट करते? दैट इज द ब्यूटी ऑफ NMR. And under all conditions, the gyro-magnetic ratio remains the same. Now, what's the difference between proton and carbon-13? We were talking about the difference between proton and carbon-13. First difference is the signal intensity because of natural abundance. The natural abundance is different. That is why the sensitivity is different. We say that proton is a more sensitive nucleus in NMR, and carbon-13 is a less sensitive nucleus. Sensitive का मतलब है easily detectable. Proton is easily detectable than carbon-13 in NMR because of its larger natural abundance. Second difference is in their Larmor frequency. If you compare the Larmor frequencies of proton and carbon-13, you will see that proton has a Larmor frequency almost 4 times greater than that of carbon-13, right? If you go down to 7.05 Tesla, the Larmor frequency of proton is 300 megahertz, and the Larmor frequency of carbon-13 at the same magnetic field strength is 75. Again, that is 4 times that of carbon-13, right? So the difference between the Larmor frequency is 4 times. The difference between the Larmor frequency of proton and carbon-13 is 4 times. What is the difference between their gyro-magnetic ratio? It's higher for proton, but how much? कितने times ज़्यादा? How many times the gyro-magnetic ratio of proton is higher than that of carbon-13? Again, 4 times. इसको multiply करें, multiply this with 4, this would almost be equal to 267. So the gyro-magnetic ratio of proton is 4 times that of carbon-13, which means that it is more responsive towards a magnet than a carbon-13. Its Larmor frequency is 4 times that of carbon-13. Its natural abundance is almost 99% greater than that of carbon-13. And because of all these differences, proton is more sensitive than carbon-13 in NMR. It is easily detectable. You can have a good proton NMR spectrum with a smaller quantity of your sample than carbon-13. The spectrum would be clear, and because of the difference in Larmor frequencies, for proton there would be a larger excess of population between alpha and beta states than carbon-13 under the same magnetic field strength. ये जो एनर्जी गैप है ना, ये एक मैग्नेटिक फील्ड के सबके लिए सेम नहीं होगा. प्रोटॉन के लिए अलग होगा, कार्बन-13 के लिए अलग होगा. Which means that if it is more sensitive, it means that the energy gap between alpha and beta state for a particular magnetic field strength is greater for proton than for carbon-13. Yes. So if it is greater for proton, it means a larger excess population. If it is smaller for carbon-13, it means a lesser excess population. Lesser excess population means less intense signal. A more Energy gap means higher access population, that means a more intense signal. So signal intensity, energy gap पर भी depend करती है. So this is how we can differentiate between proton and carbon 13 and of course other nuclei in NMR. In the next session we will talk about the instrument and some other basic things that would lead us to signal generation. Thank you.